to join me in welcoming Evert Geurtsen.
Thank you. Thank you, Bali, for a very kind introduction, and welcome everybody. And I will do my best to make it not the food that makes you stay, but rather the subject and the talk. Thank you for some of the comments on quantum computing. Just one comment I'll take issue with. Quantum computers create hype. It's not the quantum computers that create hype. It's people actually like me who talk about quantum computers and the wonderful things they're going to do. And yes, that actually is a problem. What I hope to do tonight is give a bit of an overview of what's going on out there, the general landscape, and therefore what we might expect to be the near and the medium-term future to look like for quantum computing, but also, and very importantly, what's happening in the UK. And the UK is a very, very prominent player in this science, and talk a little bit about what we do here in the UK, and also how it's possible to begin to participate in this new technology. So that's what I'll talk about. I hope to cover three things. Generally talking about quantum computing and simulation. Now, I'm an engineer, I am not a scientist. I'm not qualified at all to explain how a quantum computer actually works, so I'm going to duck any questions on that particular subject. I'm going to skim over that. But generally about, what are the claims, what are the outlook for this technology. Talk about the general status of the industry, and then talk about the UK program and how to engage. So, quantum computing and qubits, and I would imagine most people will have already had a look or have read or heard about quantum computing and this notion that it uses, and more importantly, it manipulates two key aspects of quantum physics, and that's superposition and entanglement. Superposition is the notion that you can manipulate a particle such that it goes into a quantum state called superposition, and that means it is on and off. It turns left and it turns right. It is positive and it's negative at the same time. Now, until quite recently, that was an interesting phenomenon. It is a phenomenon that was understood and therefore used, but it couldn't really be manipulated until relatively recently. But we can, quite reliably now. The other aspect of quantum physics that is used in this technology is entanglement. These particles, or these phenomena that are in this state of superposition and therefore on and off, we can connect them with each other using the phenomenon of entanglement. And that means you can actually create circuits using this the quantum theory. And once you have these circuits, you can begin to manipulate the circuits and do logical operations. And that is a quantum computer. And because of this notion that a particle or a circuit is in two states at the same time, it means that effectively you've got a bit, in the analogy of classic computing, you've got a bit that's both on and off. All my bits are both on and off at the same time, but they know what they are, sensibly, can communicate that with each other, and therefore it becomes a classic computer, but one that effectively doubles with every single qubit that I add. And that is this phenomenal scaling up that quantum computers can do, and that is the thing that gets people so excited. Because doing that, it means that you've got a computer that scales very, very fast, exponentially fast, relative to classic computing. And that means we're going to be able to, in due course, once we can build these machines at scale, have far faster computation than we can with classic computers. And that means we can solve very, very hard mathematical problems. And those problems include factoring. It's something that's very difficult with classic computers, and that's a good thing because all of our encryption is effectively based on that supposition. So quantum computers can factor quite efficiently if once you have them on scale. In fact, the algorithm was invented a couple of decades ago, long before we were even thinking about building these machines. You can simulate and solve or optimize very, very complex problems. And particularly in chemistry and pharma, in bioinformatics, material science, the notion that you can actually understand the detailed interactions within a molecule gives you the power to begin to understand what's happening and then manipulate what's happening. And that has very large promises. There's a little anecdotal hype thinking there at the bottom. I think in fairness, it comes from a very reputable group of analysts, the Boston Consulting Group. And a recent report, as an illustration, it's very small, so you might not be able to read that. Fertilizer production around the world. Fertilizer is produced in a very, very inefficient process. It costs about $100 to $300 billion per year to produce our fertilizer. And it consumes between 3 and 5% of the total world's natural gas production. We think you can make that process a whole lot more efficient, energy efficient, if you understood the chemistry in detail. But to understand the catalyst that is being used for that process, to model that in a classic computer would, and I'm not quite sure how people calculated it, but people tried. If you took the best computer that we've got right now in the world and tried to simulate this particular catalyst, they estimate it would take about 820,000 years to run the simulation. And a fully functional fault-tolerant quantum computer, supposedly, can do that in less than 24 hours. And that means you can unlock secrets of massive magnitude and have a major impact on the world. So it's speed up, it's simulation, it's solving big problems. And that includes machine learning, modeling, digital simulation, etc. So that's the excitement. We can double the power of a quantum computer with every single qubit we add. Once we worked out how to build 1,000 qubits, building 1,001 qubits can't possibly be very difficult. Building 1,002, etc. You can see where we're going. We've got speed-ups beyond the capability of future digital computing. Clearly, digital computing has got some time to go yet. But you can also see that with that sort of rate of growth in capability of quantum computers, that is going to be a whole new set of capabilities. And for that reason, it's expected to be the impact to be economic, to be strategic, to have impact on security as well. And that probably also explains why the level of interest is not just commercial. Again, this same group, Boston Consulting Group, wrote a recent report. They do some very thorough research. They estimate the impact, the value impact of quantum computing to be around $450 to $800 billion per year in operating income, albeit in 30 plus years. But still, it's a phenomenal number. And just to show that an extract from that report, so we're looking at near term, broad quantum, medium term, longer term, and it's 20 to 30 years when we're seeing these really big economic impacts. But it's not going to be 30 years until we see quantum computers working. And in fact, they're already indicating in the next 2 to 5 years, we are going to see working quantum computers with an economic benefit. And I'll talk a little bit more about that. What is relevant on this slide too is this notion here, error mitigation, error correction, modular architecture. What's all that about? So, quantum computers, once we can build them, are great. As I said earlier, it's only quite recently that we started able to manipulate particles to a level that we can reliably create superposition and entangle them and control the circuits. We're working at particle level. We're working at machines that operate at near 0 Kelvin for superconducting circuits, for example. We're working at near absolute vacuum for ion traps. So we're talking about very, very complex equipment at the moment still, that is on the whole mostly still in university labs. Therefore, quantum computers and qubits are fragile, difficult to control, difficult to read. They're full of errors, slow and expensive. Other than that, they're great. But we've got some way to go. But the errors in particular are one of the key problems of quantum computing. The error is where this special state of being a 1 and a 2, or being between a 1 and a 2, when that drops, when that collapses. And pretty much anything in the environment of a qubit can cause that collapse. So these are very fragile states. They last very short time, they're difficult to maintain, and when they collapse, pretty much the circuit collapses as well. And that means that whatever you're running on that stops being useful. So what can you do about it? Well, we've got ongoing engineering work going on to give us longer coherence times, to reduce the probability of this collapse. And secondly, there is a wheeze, or maybe it's a bit disrespectful, there's a deep complex theory called quantum error correction, and it says if you've got enough quantum qubits and you combine them with each other, you can actually build a logic that says even if one or two of them collapses, the other ones will work it out, and I have a fault-tolerant circuit. That's great. The only problem is the estimated number of qubits at current rates of precision that we currently make, we're still talking about roughly about hundreds of thousands, probably millions, maybe even tens of millions qubits to build one logical qubit. So one that we can completely rely on is a logical qubit. We need an awful lot of physical qubits. The maximum count of reliable physical qubits we currently can build stands at 54. So we've got a while to go. So, but nevertheless, there is this notion of quantum volume. And the quantum volume, as a measure of how good a quantum computer is, takes two things into account: the precision of each individual qubit, as in its reliability, and the number of qubits that you have. Between them, that gives you a measure of the performance of the computer. Also, because this overhead for quantum error correction reduces quite dramatically the more precise you make the individual qubits. And that gives you that particular setup there in that graph. So, I think we all know that we're a good while off from building these fault-tolerant quantum computers. To be able to build millions of qubits, maybe it improves, maybe it's going to be hundreds of thousands, but still we're a long way away from being able to do that. And in fact, we're struggling still to see quite the path of how we're going to get there. Other than that, we generally have confidence that there will be a way. So, up until quite recently, the thought was, well, it's just going to take a long time, but once we get there, it'll be worth it. Since then, a new idea has come along. And it says, well, hold on. If we can build 50 or 100 qubits, they may not be full, may not be reliable, but you can run them until one of them collapses. How long could you run one of those? And actually, we're beginning to find that you can run a program, certain applications, such that you can get a useful output before the thing collapses. And that is what's called a noisy intermediate-term quantum computer, called a NISQ. The term was quoted in 2017. The paper was written in 2018 by John Praskell of Caltech. And it's really opened up a whole new vista on quantum computing, because we're now still on the path towards building these many, many qubits that are reliable, that are fault-tolerant. But in the meantime, we're saying this platform of these experimental qubits actually might prove to be quite useful. So NISQ, a big term, and we'll talk about that. There are some other technologies as well. You can also use quantum computers or quantum systems to simulate another quantum system. Some of the deep chemistry is a quantum system. And you can mimic that system by being able to manipulate not that exact molecule, but a system that you can operate on a bench. Those simulators are quite useful, particularly for chemistry. We think we're going to see useful simulators before we're going to see quantum computers. So these are not digital simulations of a quantum effect. These are mimicking a natural phenomenon in another natural phenomenon. So simulators are an area of attention. And then there's something called an annealer, which is also using the quantum effects, but doesn't allow you to build a universal circuit. The biggest and most well-known name there is D-Wave, which is a Canadian company, which has been around for probably about 2 decades. They built fully working operational machines They're accessible online. They have a number of customers. And what their system do, it's not a universal quantum computer, but it allows you to find a minimum in a complex landscape. So it allows you to optimize your cost function. Anything you can express as a cost function, you could optimize using an annealer. There's a big debate, unsurprisingly, whether anything that machine can do cannot be done better on a classic machine. But we'll come back to this whole notion of supremacy, advantage. Right now, there is a company, they've got, and they're showing results. So that is another area of development. You can mimic a quantum computer using a classic computer in an emulator. And that works very well. You can build a simulator or an emulator of say, a 20-qubit machine and run that on most laptops. Actually, it's not that difficult. And there are a number of open source programs around, and that's great for learning how to program in quantum computing. The downside is that, unsurprisingly, you're going to need an awful lot of memory and storage very quickly the moment you begin to increase your qubits, because this exponential growth curve kicks in. So that means that pretty much the maximum you can emulate on a classic computer is somewhere in the 40-ish qubits. And after that, you just overwhelm whatever we have in classic worldwide. Still, it's a useful tool in the overall development of the industry and the science. And finally, I should mention something called quantum-inspired classic computing. And that goes along the lines of a scientist saying, I've got a new algorithm that I can run on a future quantum computer. And here it is. And it's machine learning in a completely new way, and it's 100,000 times faster. And I can do this, that, and the other, and it's wonderful. And then another group of scientists go, oh, that's an interesting approach. We'll look at that algorithm. We'll go back to our classic computer. And 6 months later, they come back and say, beat you. I've reworked my old algorithms, and I've just realized there's a much faster way of doing what you said you could do on a quantum computer. That's a surprisingly interesting game. Actually, to the degree that quantum-inspired classic computing has become a bit of a sizable business for certain companies out there, particularly Microsoft is playing very heavily on that thing. So those are sort of the steps. The NISQs are the one that is getting everybody quite excited now. So how all these things work? What are the technologies? Now, as I said earlier, I'm not a researcher, so this is the bit where I'm going to talk a little bit fast and mumble. But effectively, there are a number still of technologies you can use to build these machines. What is interesting, a year ago, 2 years ago, any presentation about quantum computing, this slide would have probably been the main part of the presentation, and there would have been tables about advantages, disadvantages, etc. That has a bit gone away as an area of debate, because what we know is that we have two technologies with which we can build relatively small-scale machines. NISQs can be used for superconducting circuits and ion traps, or ion traps and superconducting can be used for NISQs. And then there are a number of other technologies that we know at some stage will probably work. At some stage will prove a major breakthrough advantage relative to whatever was there before. But science will go on about those. The ones of acute interest right now are superconducting and ion traps. And that's not because they're inherently better. That is because they have near-term viability. Superconducting circuits is effectively you build a circuit or a chip with a number of circuits. Each circuit can be put into a superposition state. You put all that in a dilution fridge. You cool it all down to about zero, a few millikelvin above zero. And then you put your inputs in. Within that fridge, you can maintain superconducting. And the current count on maximum qubits there is the 54 of IBM and Google. So that's quite good. The problem with that technology is that it's clearly working. The problem is that, how many more qubits can we fit into a fridge until you run out of being able to cool it, to keep it cooled down, because at the end of the day you're operating electronics at near 0 Kelvin. So that is the balance, that is the challenge. And of course the other thing is still the noise and the coherence, to keep those things in that delicate superposition state. The ion traps are a different approach. There's a picture there of what is the Oxford ion trap. If you look really close at that picture, and by the way, that picture is made with a normal standard SLR camera, you can actually see the light coming off the single particle that is held suspended in that field. And that's what ion traps do. They take a number of particles, they suspend them in a magnetic field, they cool them down, use a laser cooler cooling. In fact, the ion trap itself is at room temperature, but at near absolute vacuum. So it's difficult again, but again they work, and there's good confidence that we're going to have workable NISQs using ion traps very soon as well. Some of the big proponents of ion traps are Honeywell, IonQ, Universal Quantum, Alpine Quantum Technologies with Atos backing. So there are a number of companies working on ion traps. Superconducting is Google, IBM, Rigetti, Intel, and a number of others. And then there's photonics, solid state silicon, of course. We know lots about how to mass produce silicon really, really cheap. If we could ever do a quantum computer in a silicon circuit, that'd be fantastic. It'd be scalable, but it's some way off. NV centers in diamond, it's another solid state technology that is beginning to get very interesting, but again, quite a long horizon. And then topological particles, which are very interesting because that's a theory that actually has the error correction built in. The theory is predominantly being developed in Delft in the Netherlands with Microsoft backing. Very interesting technology, but also still one that is still quite a long way off. So they have different time horizons. We think all eventually might be able to scale to universal fault-tolerant computers, but the first two are the ones for NISQ computers in the very near future. So we talked about NISQs. I've mentioned inspired. There's quite a few words. The big word is quantum supremacy that you may have heard about. It was a word invented in 2012. Maybe the world was a better place in 2012 and supremacy wasn't quite such a scary word as it is in today's world. I think there is a general agreement that it is an inappropriate word for two reasons. First of all, the associations with supremacy per se, so therefore it's an unfortunate word. Secondly, it implies that at one stage we're going to build a quantum computer that is better in every respect than a classic computer. And that is actually quite unlikely. Quantum computers at any time in the future are likely to be very powerful machines, but it's unlikely that they will completely replace classic computers who are hugely accomplished machines and have got qualities that are unlikely to be displaced by quantum computers. So it is an unfortunate term. It is also a very vaguely defined term. It was defined long before the notion of NISQs. It was defined by the same gentleman who mentioned NISQs. He also came up with the term supremacy. But he was still thinking very much about fault-tolerant quantum computers of the future, and therefore he didn't define it very well. So really where we got to is quantum supremacy is now to be understood as something that can do something that you cannot do on a classic computer, whether it's useful or not. And that's great, and we'll actually see that there's a claim from Google that supremacy has been achieved. And I've got a slide about that in a little bit further down the presentation. As a user, that's great. So you've got supremacy. But it'd be nice if I actually got something useful out of a computer as well. So different terms have come along. There's one called quantum advantage, which is in many ways worse than quantum supremacy because it's really ill-defined. For some people, it means supremacy, but something useful. For others, it means just something that I get value out of, whether it's better or not. So it is a term that is quite widely used, but sadly rather badly defined. And then there are new terms as well, quantum-inspired, we talked about. This is this notion that you can do something in theory, and then you go back to classic computer, improve that, and then you've got a quantum-inspired algorithm. Quantum practicality, quantum value. That's the business saying, I really don't care whether you can verify that this thing I'm doing on this quantum computer is actually impossible to do on a classic computer. Right now, I've used a D-Wave computer, and I get a result that's better than I got yesterday on my classic computer. To me, as a company, that's value. If in 6 months from now, one of your PhD students come back and say, well, you could have done it on a classic computer all along, it's 6 months later, and I don't have too many idle PhD students sitting around in my business. So that's this definition of value that is challenging the theorists in research. And, the theorists in research saying there is no point in trying to push quantum computing on the basis of, hey, I've run a program and it does something that I couldn't do on my classic computer, if you can't actually prove that. Because we may be wasting our time and we may be misdirecting the development. Whereas business says, that's fine, but I don't buy that argument. I just want something that runs faster. And it's an interesting tension. And it's a tension, of course, that is very relevant for companies like IBM and Microsoft and Google, who are out there right now selling their wares. And what's particularly interesting there is that for the theorists, a NISQ machine, a NISQ output machine, is actually quite hard to prove to have an advantage. So you can do something that seems faster, but proving it in theory is actually quite hard. So we might be running for the next few years on machines with lots more hype that seem to be doing things faster, with still quite a lot of dispute whether they actually are faster or not. But, as we said, certain applications better need not be perfect, and just using a quantum machine and learning how this thing works in anticipation of a faster one tomorrow, that in itself has value too. So, practicalities to get to that quantum advantage, to the point where we can actually get economic value from using a quantum computer over using a classic computer. Let's take that as a definition. Well, we need more qubits, we need cheaper ones, we need hybrid systems. Quantum computers, you do not want to waste any quantum resources on putting a nice window on your computer screen. All of that stuff is done classically. Classic machines are reliable, they're cheap, and they can do all the mundane stuff. We need a full software stack that goes from that very delicate hardware all the way to a user interface. We need algorithms and applications. There are quantum algorithms, quantum computing algorithms. Most of them have been written in pure theory for machines that are fault tolerant and therefore still 20 years away. What we don't have are algorithms and applications for these noisy machines. And that's actually might be as big a problem as having qubits right now. And that's why you will see there's a lot of pressure now in the industry to get people to use these early machines, because only through use and by creating a user base do we think we're going to invent the algorithms and the applications. Of course, to do that, you need a development environment. It'd be nice if you didn't necessarily need to be a PhD who understands linear algebra and tensors and all this other good stuff. If there was just a development environment where you could just begin to address these machines in a more traditional user interface. We need quantum networking. These computers have to begin to talk to each other. That would be another way of scaling up. We need standards because we need to begin to define what all of these things mean so that we don't waste too much time in either development or use. And as I mentioned, we need user communities and skills. Now that picture that's there is to break up a lot of words from the slides and to make it a little bit more appealing. But actually is also, we'll see that picture in a bit, because that picture is the work package content of the National Quantum Computing and Simulation Hub. So in other words, all of those things we realize we need to do, and we are. Users, of course, the user community that is being addressed first and foremost by the companies that are investing heavily in quantum computing are the obvious users, the high-performance computer users. Finance, engineering, chemistry, pharma, and the science community itself. Those are the people that are being confronted right now by salespeople. That is the first community that is likely to spend money to get access to quantum computers. But, of course, what these people will do is they say, well, I've got this problem that I currently are struggling to solve in classic computing. It takes a long time to run this routine. There's a couple of things I just cannot do in my classic computer. But these are still traditional classic computing problems. So in some ways, we're kind of making quantum computers just a faster classic computer. There's another approach, and we're seeing that particularly in the startup community, that says there's some stuff that we currently are not doing with computers at all, because it just simply hasn't occurred to us that you could do that with a computer. Those are some new ideas, and those are the disruptive ideas, and that might well be of the acute interest. And as I'll show, there's some different perspectives in industry on this as well. Important users as well are governments and national services. I'll talk about encryption, but beyond encryption, there are some other big problems that these machines might be able to solve. So it shouldn't surprise us that governments in particular are looking at both the prosperity aspect of quantum computing, as in what can it do for my economy if we're going to be proficient users of these machines, but actually also what might it do to my advantage as a defensive company, as a defensive nation, but also what might it do in the hands of an adversary. And that is an important issue. To help all that, we run quantum readiness programs. The companies engaged in quantum computing, the national programs, online access. You can get access to a quantum computer right now. There's several options there. And what we're seeing increasingly too is there actually is a business emerging, not in quantum computers, but about quantum computers. So we're seeing a proliferation of conferences of 2-3 days that are addressing the corporations that we think are going to be, that are thought to be the future users and are beginning to pay money. Encryption was mentioned. So, as I mentioned earlier, quantum computers will be able to factor large numbers. And that means that at some stage, they will be able to break some of the current encryption methods. That's not an immediate concern. NISQ machines, ones with a 50 or 100 or 200 qubits, are not going to be able to do any of that. It's not a threat. However, it is, what is a threat is that you can store current data encrypted with classic methods, keep it stored for 10 years, 15 years, and then once you've got that universal fault-tolerant quantum computer that can do factoring, then apply that to that data, and you'll find out what was encrypted data 15 years ago. Who cares that, I might have had a bad credit bill 15 years ago? Well, actually, there's quite a lot of data that in that sort of period becomes highly sensitive. And for that reason, and of course, the problem is, it takes time to take a load of data that is currently encrypted with current methods to re-encrypt that into a new method that is post-quantum safe, so you can be confident. Do we have enough time? It depends on how long it takes to encrypt current data, and it depends on how soon these quantum computers are going to come along that are going to be the threat. If one is going to arrive before you're done, you've got a problem. And the other problem is that there are some methods that we can be certain that they will be vulnerable. There are some other methods that we think are going to be fairly robust for a bit longer. What we don't know for certain is which method will definitely be post-quantum safe. And for that reason, NIST in particular is running a competition and is inviting theorists and companies from around the world to submit methods. and they will they apply their knowledge on that and try to assess them for being post-quantum robust. The problem with the practical problem with that is, in the meantime, until we know which ones are going to be robust, there is a risk that companies are going to re-encrypt data with more advanced methods that they might not quite understand and actually introduce a bigger risk than if they had just left it alone and waited. The National Cybersecurity Centre in the UK is giving advice on this. They've written a white paper that is available online. If you are involved with encryption, if you are in an organization that does have confidential information, I would be fairly confident that you already know about this subject, but it is one to be aware of and to start working on now, because it is a future problem whose consequences are here today. So, who's playing? Well, the ones you will have heard of are the big technology vendors, and we'll have a look at a few of those. National programs, for reasons I've explained. New entrants, so existing companies that are moving into this field. Lots of startups and lots of research institutions as well. Amongst the national programs, some of the biggest ones, the European Union has been running a quantum technology flagship. The flagship has 1 billion euros of funding, but remember that sits on top of all the national programs in the member states. So 1 billion euro actually hugely understates the amount of spending that Europe is doing in this technology. Europe is perhaps having learned from classic computing and digital computing and observing where that industry sits today, is making a very determined effort to be a major player in this field. And therefore large amounts of money and large amounts of political support is being put into this field. Individual member states, early starters, Denmark, obviously with its history in quantum physics, was an early starter, although their program is fizzling out a little bit. The Netherlands have got a very large and ambitious program, and in fact we've got large inward investment from both Intel and from Microsoft. Germany is gathering speed, and they've announced 635 million euros for their national program on top of their share of the flagship. France is due to announce a national program. Poland has a national program. Sweden has a large national effort, etc.
What about China?
I'll come to that. The UK, we will talk a little bit more about the program in the UK, but it is one of the largest programs in the world in the UK. The USA have come to the party very, very late. They clearly have got an enormous science community, very, very competent in this field. Individual institutions have been long engaged in this technology, and of course they have their big tech industry. But as a national program, they've only really started coordinating in 2018. And we're still in the very early stages of getting organized. So the American program is very, very large, but very, very fragmented as well. China, you asked. China, indeed, we've seen many announcements. The Chinese national program, in fact, started very, very early. 2006 was the first announcement of a national quantum technology program. Clearly, China is a large country. It's very well resourced. It has a lot of very smart people, a number of great universities. They seem to focus on quantum communications before quantum computing. There are a lot of papers being produced. There are very large amounts of patents being filed in China, but numbers don't say everything. It's for us increasingly hard to assess where China is in their technology, particularly in computing. Other than to say that we have to be highly aware of their resources, particularly the number of smart people and the number of very large companies in China as well. Huawei, Alibaba, Tencent are all big investors in this field, and are certainly spending at least as much as the Googles and the IBMs and the Intels. And then Japan, Canada, Australia, Singapore, Russia, India, all these countries have got national programs that are funding research and are connecting that research into their industry and have national interest programs there as well. So national programs are a big funder of this technology, partly, of course, because it's expensive and it's an expensive game to play in, and therefore there are not many companies who can afford to engage. Nevertheless, there are a number of them. Slug of water. We have a number of large companies engaged in this field. IBM, Google, Microsoft, Intel are all big spenders and high-profile players. And hype, probably the largest sources, or some of them at least, the largest sources of some of the hype. Amazon have just entered into this field. Atos in Europe is a big spender and has got a very, very large and important quantum strategy. In China, Alibaba, Huawei, and Tencent are all known to be big investors in this field as well. They follow quite different strategies, as we'll see. There are a number of pioneer startups, companies that started some time ago and have actually grown to be quite large already. D-Wave in Canada, I mentioned, started building annealing machines nearly 2 years ago. They're a well-known name and they've got a large customer base. About some 200 companies that either are buying some time on their machine or at the very least are running experiments on their machines. Rigetti is still a startup, but managed to be one of the early starters and raised large amounts of money. Rigetti are developing superconducting full-stack quantum computer systems. And IonQ is probably the largest private company working on Eintrap full-stack systems, also in the US. Honeywell is an interesting company, have got a new large division in quantum computing, developing Eintrap-based full-stack computers. We probably know Honeywell from instruments and from thermostats, but they make precision equipment. And they've been working on quantum computing for nearly 10 years, public only for the last 2 years. But they've got a very large group of people working on this technology. And then there's a large and growing field of new ventures for systems, hardware, software, and consulting. Consulting is I mentioned earlier the encryption problem. Well, guess what? There are an awful lot of companies that are be happy to advise you on your post-quantum strategy. So that's a growing industry. Enabling technology providers. Things that were very, very exotic a few years ago suddenly are becoming in high demand. A dilution fridge, well, suddenly that's big business. That used to be something really, really rare in any lab, something that could go down to a few millikelvin. Suddenly there are hundreds, if not thousands, around the world being built of these things. High precision lasers, optical waveguides. There's a lot of enabling technology providers. And the good news is a lot of those are actually UK-based companies. We've got a large photonics industry, we've got a large high-tech industry, and they are benefiting from this new industry. And then commercial users are spending money. Companies are now buying time on these systems. They are buying time from consultants. They are buying time from the software startups that are beginning to advise them how they might migrate some of their biggest problems into the future quantum computing arena. In terms of spin-outs, a website called Quantum Computing. I'm out of sync. Spin-out count. Quantum computing spin-outs in some of the major parts of the world. A couple of interesting points. You actually see that Europe is keeping up with the US in creating new ventures specializing in quantum computing. Not just in general ventures, but also in hardware, so in systems. And the UK, given its size, is boxing well above its weight. And again, particularly in hardware. We have 5 startups in the UK who have raised money, who are building full-stack quantum computing systems. So quite an interesting picture. But of course, these are startups, and they don't count big tech. Big tech is very busy, and of course, what's happening too is that, as I said earlier, one of the big missing links at the moment are applications and algorithms for NISQs. And to create those, you need a user community. You need people to start thinking about that, have a motivation to make money, so they want to use your platform. So, undoubtedly, so what this chart shows is these are the providers of platforms: D-Wave, Google, IBM, Microsoft, Rigetti, Amazon, and Atos. All provide platforms that you can have access to as a developer now. And those are, these lines are all quantum software development companies around the world. First of all, there's a lot of them. They've all managed to create companies, attract money, bring in staff, and this is expensive staff as well that they employ. Some of the largest ones are UK-based. Cambridge Quantum Computing is one of the largest quantum software companies now around. Similarly, Riverlane is growing very, very fast. Facecraft, Racco. So these companies are doing very well, but you can see those companies are using systems from these platform providers. The one that stands out as definitely attracting the largest user community is IBM Qiskit. That is definitely the one that's well ahead of others at the moment. Yeah. But of course, these platform providers have got an interesting technology, interesting approach. IBM is quite clear. IBM says, we built the hardware, we built the development environment, we've got the customers, and therefore, if you're a developer, come and use our platform and help us to develop algorithms for quantum computers. It increases our market share, and you as a developer, you get access to our user community. IBM owns its environment. There's companies who have some variations on that. If you're Amazon, Amazon hasn't built, to our knowledge, its own platform, but they say, we do have a lot of customers, and we have this cloud service. We can do all this hybrid stuff. We've developed a development environment to write quantum software in. So you can, as a development software, you can come to us, but also as a hardware provider, you can come to us as well. And we'll plug you in the back of our development environment, and then you get access to all our customers. And you get access to our software community as well. So that's the strategy of Amazon and Microsoft in particular. Rigetti sits somewhere in between that as well. So you can see these companies are trying not only to develop hardware and development systems, they're also actually trying to control the market already. And that's this slide here. So IBM Q, as I said, definitely leading in terms of user community. They have a number of systems up and running. Their largest machine runs on 53 qubits. They use a superconducting system. They have their fully integrated service with their own high-performance classic computing, with their cloud services. You can access it online. They have a complete software stack and a dedicated Qiskit environment to write quantum software in. They have the IBM Q Experience, which is free. Anybody around the world can use it. They have a very large user community. Some very interesting statistics they draw out of that as well, as in who are the users. There's apparently a very large teenage user community of quantum computers already. And then they have an IBM Q partner network where you buy privileged access, which means that you have to pay, but then you don't have to part with your IP if you use their machine, and you get some privileged access to the machine in the running time as well. There are 100+ organizations, include research institutions, universities, commercial users, development partners, and educators. IBM Q has revenue from its systems today. And then here's a completely different strategy from Google. So you can see IBM says, we're addressing our existing market. And what we're telling that market is quantum computing is an addition to classic computing. And in fact, for you, we're going to make it pretty much invisible and seamless. You're going to have a classic system running in the cloud that will have a CPU and a GPU and a QPU, and it really doesn't matter to you at all. And we have a development environment that is all the user interfaces that you're familiar with, and we're just adding libraries of quantum development environments and quantum software. That's a nice continuous business, and you can see that makes a lot of sense. And it appears to be working very, very well as well. Google, on the other end of that spectrum, takes a very different perspective. So first of all, where are they? They've got the Sycamore system with 54 qubits, superconducting. It's integrated with their classic systems and cloud service. They have a complete software stack, dedicated circ environment. But their strategy is quite different. They are not going around with salespeople selling time on their machine right now. They don't have a user network. They have a very small, focused network of scientific collaborators. Some of those scientific collaborators are companies. Daimler-Benz is a quoted collaborator. And what Google says, we think this is not a continuation of computing as you know it. We think this is disruptive, hugely disruptive. But it's going to be disruptive only if we make these scientific breakthroughs. And for that reason, they're not going around signing up a large network. They're actually focusing very much on finding specific people that can help them make those disruptive inventions. So a nice contrast, an interesting different approach, and interesting to see what that looks like in 10 years from now. So they're pursuing a 10-year roadmap for realizing 1 million physical qubits. And with that, you should be able to probably at that stage build logical qubits. And they have a business goal today is to discover transformative applications. So the hardware is a means to an end. It's the applications they're looking for rather than selling the platform. And they're focusing on scientific collaborations with companies, institutions, and they partner with a lot of software developers as well. And Google did something else. They declared supremacy. I don't know if any of you have seen that announcement. So that was, I think, about 2 months ago. And the reason I'm not precisely is that the paper was published unofficially, then withdrawn, and then reappeared officially a couple of weeks later. It caused some consternation because that's very, very unusual in the scientific community for a paper to be published and then withdrawn. But there we go. Once it was there, I think the consensus was that this really was a breakthrough achievement. What they did is they took their 54 qubit processor, of which only 53 qubits worked. Nevertheless, that was good enough to run their experiment whereby effectively they gave the machine random instructions and drafted out random numbers. And that may seem a very odd thing to do, but you can then verify the randomness in those numbers, and that is actually quite significant. And you can then say, if we had done the same thing with and that experiment, getting to a defined result and a controlled result took 200 seconds. And they claimed that had they done the same calculation using their very best supercomputer, it would have taken that computer 10,000 years to produce the same result. And fair enough, that's a fair measure of supremacy. Of course, 2 days later, IBM came back and said, well, I think you're exaggerating. We just, only within 2 days, we reckon we could have run that same thing on our classic computer. It would have taken us only 2.5 days. Who knows? Where we are is that, 200 seconds, 2.5 days, 10,000 years, who knows? What we do know is that here's a machine that is beyond the capability of classic machines to be emulated. We cannot emulate reliably 53 or 54 qubits. You can give this machine instructions and a predictable result comes out. So we can control quantum computers. And they do something that has limited, but nevertheless, real-world use. And that is generating verifiable random numbers. So in that respect, it is a big milestone. And it proves that you can build quantum computers using the phenomena from quantum physics, and that you can probably do something useful with machines that are not fault tolerant. So that was quantum supremacy. And of course, the world rushed to claim it. I know I say the world, Google claims supremacy, the President of the United States claims supremacy, and quantum computing as well. But fair enough, it was a big achievement. So where are we in the UK? And we're talking a lot about big tech. We're talking a lot about big national programs, about progress. What's happening in the UK? Well, the UK is actually one of the original strongholds in quantum physics and quantum theory. We have a very, very long outstanding history of outstanding science and quantum technology pioneers. The first person to define a quantum circuit-based quantum computer was actually David Deutsch in Oxford. It was here in the UK. The theory of quantum error correction was developed by and co-developed by Andrew Steen, again in Oxford. Cavendish in Cambridge have got a long history of pushing quantum theory and quantum computation and quantum algorithms. So on that basis, and of course I mentioned earlier, we've got a very, very strong high technology sector as well. So back in 2013, a delegation of science and industry went to government and persuaded them to start a national quantum technologies program, and was successful in persuading government to start that. So we started in 2013 with an integrated national program, and we were, as such, one of the very, very first nations to do that. There was a Blackett report, a government report about technology in 2017, which confirmed that the UK was making good progress and that the technology now had real-world prospects for economic impact. And we're talking about quantum technologies in imaging, in sensing, in communications, as well as computing. The House of Commons, Science and Technology, did a major inquiry into the same field and looked at the national program, and they were very positive about what it was achieving, also on a relative international basis. Sir Peter Knight, Professor Ian Walmsley, as two early proponents, scientists in the UK, wrote a paper, and out of all of that, we've completed the first 5 years of the national program and persuaded government to continue to fund this program. So we're now going from a 5-year program to a 10-year program, and total funding of the UK program stands at £1 billion over that 10-year period. And as you saw earlier, if we then begin to look at some of the impacts of spin-out companies, of engagement of industry, we're really beginning to see that we are competitive in the world. The program in detail, what it looks like, we have 4 technology hubs across 4 focus areas. So it's quantum computing and simulation, quantum communications, which is the hub that is working with BT on a quantum internet, effectively, that currently runs from Ipswich to Cambridge, from Cambridge to Bristol. So again, it's a pioneering network. We have a skills and training program. We have an industrial challenge fund for industry-led innovation, and that includes quantum computing. So if you're in industry and you want to engage, there are a lot of money and a lot of support from government to engage in this field. We are going to build a national quantum computing center. We have specific program grants and prosperity partnerships. For example, Google has a large partnership with Bristol University and UCL here in London, working on quantum algorithms. We have government support and a policy on quantum technology. We have ongoing dialogue with other international programs. In fact, a lot of programs are coming to the UK to see how we're managing to keep this integrated and avoid fragmentation that we're seeing in other countries, which we take as flattery. And there are a number of strategic partnerships of Google and IBM at the national level. I mentioned the hub, so that's me. We used to be NKIT, the national, the Networked Quantum Information Technologies Hub. We've actually transformed ourselves into the Quantum Computing and Simulation Hub because we've gone from phase 1 into phase 2. So since December last year, we are QCS. We're focusing on quantum computing and simulation technologies. We have a 5-year program for research and technology. We have 17 participating universities with 43 co-investigators. It is led from Oxford. It follows on from the 2014-2019 program, and we're part of the national program, which is a 10-year, £1 billion program. And we as well as doing research and technology development, we do user engagement, we engage with companies, we're trying to persuade them to engage with this field. We do responsible research and innovation. We want to know what the impact on society and individuals in society might be of this technology. So we're trying to project that. We're also, out of that basis, we can make sure that we have a positive societal impact. And this is not a threatening technology. And we're working on communications to begin that process of creating a quantum literate nation in the UK. The objective is to create a quantum information technology economy in the UK that is competitive. So, and in terms of research, we're working on all those themes we mentioned: NISQs, universal fault tolerant, simulation. You saw that block. So, we're working in terms of hardware on cold atoms, all photonic simulators, superconducting circuits, trapped ions, diamonds, and silicon. And that's because we believe that all of these technologies are going to be relevant, possibly at different timescales, but we need to make sure that we maintain leading science and leading technology in this country in all technologies. And then we're working our way all the way through up to the software stack towards these outcomes, which are simulators, NISQs, and universal fault-tolerant computers. Those are the universities that are members of the network. So that is a very broad representation of the top research universities in this country. We have a number of industrial partners, and that's interesting. Some of those are enabling technology partners. Some of those are future users of quantum computing. Some of those are international platform providers. They all want to be part of this technology program in the UK. So they're all putting resources and support into this program. I mentioned we do user engagement, so we work with industry, we organize industry event dates, we sponsor hackathons. There's one coming up in UCL, so if you want to have a go, I think it is the very beginning of April for 2 days. We have what's called the Quantum Readiness Program, which is where we're addressing the very senior members of management in UK-based organizations to try to encourage them to support their data scientists who want to learn more about this field. We write reports for information, we develop partnerships, we support commercialization into spin-outs and licensing. We do international promotion of the national program to try to encourage researchers, investors, and future customers to come and have a look at what's happening in the UK. And we sponsor public engagement. The center, so this is the hub. What I spoke about is the hub. This is where research and technology development happens, mostly driven by universities, but in collaboration with industry, to make sure that we can transfer this technology into a scalable quantum computer. We'd love to see that done by our startup companies, but those startup companies are going to struggle to find their first customers. So we're relying very heavily on the investor community to support startups, to give them one of the best ways of we think we can support them is by creating a national quantum computing center that will build scalable quantum computers. So they will be, in all likelihood, the first customer of many of our own startups. And that way we can create this procurement cycle that will help our early technology providers and give them a step up. It also builds a national facility where we can have advanced platforms that developers and users can use to get access and learn about quantum computing and learn to use it. So that center is, interim management has just been appointed. That's likely to be announced probably this month, and I'm sure you will hear a lot more about that. It's probably one of the most ambitious technology plans of the UK government for quite a few years. Which leaves us to, is the leap. And I'm not talking about a quantum leap. Is this a disruptive leap? Or is this just computing as we know it, but just faster? And as I've illustrated, it suits the narrative of certain incumbents, and they may certainly not be wrong to say quantum computing is absolutely fantastic. It's going to be faster. It's going to let you do things you couldn't do, you couldn't dream of doing with current computers. But quite frankly, that's no different from going from a Colossus to a personal computer to an iPhone. You know, that same migration path, and quantum is just part of that. And maybe it is. Or we might just find some applications for quantum computers that we had never realized you could have a computer do. You know, different types of problems, different approaches, different controls in particular. And controls is one area of great interest. Could you have a situation where you have a chaotic system and you can use a quantum computer to help you control chaotic situations? And that's, for example, something that might well be very disruptive, very unlike classic computing, and therefore transformative. And I'm sure you'd rather have a drink or something to eat and take a vote, but the future will tell us whether this is going to be a big leap or a quantum leap. And with that, thank you very much indeed.
Maybe take some questions.
Yes, certainly.
Do you have any questions?
Well, on entanglement,
Mm-hmm.
how close or how far apart are we entanglement?
Well, it depends a little bit what technology you use. One of the breakthroughs that we've managed to prove in the previous technology hub in NKit is remote entanglement of ion traps. So you build one ion trap with one set of superposition qubits, and then you build another one over there, and you connect them photonically. You go light matter on both sides, and you can actually transfer quantum information between the ion traps. And that means you can build a scalable circuit, because now it's a matter of money and the size of my warehouse of how many qubits I can build. There's a downside to that, and it's other than the obvious complexity, is that it's relatively slow. But you know, we have got the highest speed and the highest precision in 2-qubit remote entanglement in the UK, which is another first and another leadership indicator of the UK.
So my paired encryption's a way on.
Sorry?
My paired encryption's a bit of a way on.
Yes. Well, that's another challenge, because that's, you know, that goes back to the notion of having repeaters and quantum memory, which is another missing link in all of that. Yeah.
What is the current recommendation on encryption now, considering the quantum?
Yes.
Just readings. What's the current recommendation on encryption or algorithms? Currently, mostly we use AES.
Well, let's say this with caution. Because I am not an expert, and I don't want to put words in the mouth of people who are experts, which are the National Cybersecurity Center. There's a link that I would recommend. But as I understand their advice right now is in saying, use best practice that you know and understand. As in, don't go into something that you're being told is better, but you do not understand. That is a risky strategy in itself. But also, don't be complacent and keep using what you're doing because you're comfortable with it. Use best practice as you understand it, I think is the easiest way to summarize it.
Evert, I have a question.
Mm-hmm.
All of the information that's coming in from space, Hubble telescope, etc., is quantum computing being used to process any of that, or is that all traditional?
No, one of the areas of great interest is indeed is space. ESA is one of the parties that is spending time on understanding quantum computing and its impact. Obviously, Earth observation data, or for example, the alien life detection programs, very, very large data sets. We think quantum computers are going to be very, very good at detecting patterns, but not right now. One of the big challenges for quantum computing is the ability to hold and keep data, because you need to keep it in quantum form. One of the things we don't have yet is quantum memory. It doesn't exist yet. There are some paths towards quantum memory. So that means large data sets at the moment are a no-no for quantum computing. What you can do, and this is one of the paths that some of the quantum machine learning companies are proposing, is that you can do large data set processing and learning in classic, and then you can feed that detected pattern into a quantum computer and then feed data strings through that, and it'll recognize the patterns faster than the classic computer can. So, but that is one of the challenges, and so something for the future.
This might be the same question, but is quantum computing applicable to neural networks?
Right, I'm firmly stepping outside of the area where I should have comments. But yes, there is quantum learning and also using combinations of machine learning and quantum processing. There are some very promising paths. Because of course, some of the areas of great near-term interest are dynamical mean field theory for chemistry, computational fluid dynamics. These are computation-heavy processes, and that's what quantum computers are quite good at. So if you can use classic computing to do the build the tensor networks and then present a relatively small data set but with high processing intensity to a quantum computer, that is a nice combination, it seems, for the near future.
What threat do you see this poses to cryptocurrencies and the whole SHA-256 sort of breaking down? It's going to
I really don't know, and I honestly can't comment. There are a lot of headlines around, is quantum going to make all of this blockchain hype, which hey, it's hype versus hype. It's I honestly don't know, and I've not heard comments from our research community that would give me a confidence to say yes or no, it will break it or not. I would imagine, of course, there's a flip side to quantum being able to break encryption. Quantum also gives you absolutely unbreakable communications in the future. This is sort of outside the field of quantum computing. This is quantum communications. But what we'll be able to do is communications from A to B, and that is absolutely beyond interception. If you do intercept it, it absolutely will be known to the sender and the receiver. So that's the flip side of quantum being a threat to encryption. Quantum also will give some very new ways of encrypting and making data communication secure.
There seems to be a lot of duplication of effort with all these organisations and countries. Do you think a community will develop, international community, where they start sharing knowledge which will spread the knowledge and reduce costs, like I think's happened in other scientific areas?
Yes, there is a good point. And I think in fairness, pretty much up until now, or maybe until very, very recently, most of this has continued to be driven by the research community. And researchers on the whole around the world are good at collaborating. They write papers, they share information, they visit, they travel, they exchange. And therefore, that's been very much the picture. What I think is fair to say is that two factors are beginning to put some pressure on international collaboration. And that's the first one is growing international interest, or growing commercial interest. So, and in some ways, in the UK, we have an advantage of not having a large big tech community. Because what we're seeing, for example, in the US, is that a Google or an IBM can pretty much drain a physics department overnight. It's silly salaries, and next thing you know, your science department walks out and moves into a Google office, and then they're inaccessible as scientists. In fairness, actually, Google is pretty good at keeping information public. So that's one risk, the commercial pressure. The other one is a growing security aspect to quantum technologies. And there's nothing that we can do other than to say, look, we're still a research community. I am an employee of a university. Our universities would struggle without its research and student community from around the world. But nevertheless, we also have to acknowledge that there is an important security aspect to this technology, and therefore, that is going to reduce the sharing that there has been in the past. Having said that, as I said earlier, let's not go into Brexit territory, but EU flagship has 14 funded technology programs. 12 of those have got British participation from British universities and British companies. The US and the UK are actively looking at co-funded programs. The US, Canada and the UK, we have exchanges about our programs where we're looking at the possibility of co-funded research. So there is still a lot of positive international research too.
Penultimate question.
All right, thank you. My working life has been very different to that of my parents, and that's largely due to technology. I'm trying to envisage how the next generation's working life will be different to mine. Do you have any thoughts on that in respect of quantum computing?
Well, I don't know, I honestly don't know what the world's going to look like with quantum computing in the future. One of the things we can do, and we really think we should do, and in fact we are part of that, we are doing, is to make sure that at least we have a broad understanding and comfort with quantum technologies in the UK as across the whole population. So for that reason, we do small things. We go to science festivals, we have little experiments, we have an open quantum technology showcase once a year. But we also we're promoting at the moment the idea to the national program and decision makers to start maybe a program around making the UK a quantum literate nation. Let's drop these silly words of spooky and this is all too complicated for you to understand. Actually, this superposition makes as much sense as a bit in a transistor. It's all a bit magic if you don't understand the physics. But that doesn't mean yet you have to perceive it or experience it as a threat. And I think this notion of very broad education and comfort with quantum technology, I think, is going to be very important, because we can't tell exactly how things will change, but at least make sure that it's a fair change for everybody.
Okay. Final question, anyone?
Yep.
Thank you.
Because of this, amazing limitless power. When you think about, all the data centers we have today in the world, which is, I don't know, consuming 10-15% of world energy, do you think that quantum computing could also be a solution actually to consolidate all this huge estate of computing power we have today?
It is definitely a thought that is playing in the minds of the research community. Yes, because of course you could say, well, we're going to use quantum computing on top of everything else we have, and therefore it's going to make everything fast. Or actually, it might displace, as you say, the very fast-growing energy consumption, in particular, of the growing installed computer base, and therefore, now right now, a 54-qubit machine running at near 0 Kelvin is not particularly energy efficient, as you can imagine. But you can imagine exactly as you say, once we get to these scalable machines, that you might well say, actually, we haven't come up with a dramatic breakthrough transformation of computing, but what we can do is do the computing we do in a much more energy efficient way. So, yes, that is definitely a consideration.
And the world only needs 5 computers.
Yes, of course. Good. Thank you very much indeed. That's very enjoyable. Thank you, Valen.